The rainforest had a rhythm that the uninitiated heard as noise, and the practiced heard as pulse. In the heart of the Sierra Verde Basin, where the canopy stacked like a living cathedral, and the soil breathed damply beneath decades of leaf litter, the research team arrived carrying gear in backpacks, in crates slung from the backs of porters, and in their own expectations. The project was ambitious: to install a permanent, lightweight canopy observatory network in one of the most biodiverse yet geologically temperamental sections of the old-growth forest. They were there to understand the dynamics of canopy collapse, what preceded it, how the interconnected trees distributed stress, and how climate-driven shifts in precipitation were changing failure modes. The loss of a single emergent limb didn't just mean fallen timber. In that vertical world, it could mean a cascade of consequences: disruption of arboreal species, shifts in light regimes, and the end of a multi-million-dollar long-term ecological dataset. Dr. Elena Morales, the principal ecologist, had built her career on reading the language of trees. Her hair, threaded with silver from many nights spent in the wild, escaped her headband whenever the humidity spiked, and her voice had the calm cadence of someone who had watched systems teeter and then self-correct. Rahul D'Souza, the botanist, was a stoic graduate student whose notebooks were dense with diagrams of root tensile patterns. He muttered to himself in soft Hindi when trying to model the strain redistribution in living wood. Jana Kuiper, structural engineer turned canopy architect, had metric sketches of rope tension, dynamic load factors, and failure probabilities taped inside her waterproof binder. Mateo, the local guide, spoke in low tones about the forest's moods, and had quietly convinced the skeptical grant committee to allow him to act as liaison with the mountain's traditional custodians. Lila, Elena's newest protege, and a graduate student with an overfull curiosity for biotic feedback, had a logger full of sensor code, each line written to pick up micro-vibrations in wood, the whispering cracks before something let go. Their base platform was to be suspended 50 meters above the forest floor, anchored to 4 emergent trees with minimal hardware: hybrid fiber cables, dynamic slack-adjustable shock absorbers, and a web of secondary soft lines that would allow the platform to breathe with the forest instead of fighting it. In the weeks since their arrival, they had installed acoustic strain sensors inside select limbs, fiber optic cable for distributed sensing of tension, and a mesh of aerial bridges for moving between observation towers. The forest, in its vast patience, had accepted them with the reluctant tolerance of something that knew its own longevity. High above the platform, near a cluster of canopy giants, lived Tico, a middle-aged three-toed sloth whose existence had been a quiet ghost in the trees for years. To the villagers in the valleys, he'd been a slow-moving myth. To the occasional tourist, whose map pointed in the direction of sloth sightings, he was a charm. No one had intended to involve Tico in their work. He moved with the deliberate economy of a species whose survival depended on being unnoticed. Tico had claimed a large ceiba tree as his center of gravity, a tree with buttressed roots like the base of a cathedral column, and a crown that towered in the emergent layer. The tree's limbs arced and intertwined with neighbors through a lattice of lianas, vines, and epiphytes, creating a complex mechanical network centuries in the making. The week had been heavy with rain. The saturation in the soil had increased the pore pressure in root zones, and the weight of water carrying the new growth in moss and liana was non-trivial. Jana's readings indicated elevated baseline tension in several of their primary anchor limbs, the kind of quiet drift that, if left unobserved, could become a prelude. They had a weather window. A storm front was forecast to arrive in 2 days. Their models predicted wind shear crossing the basin in gusts that could push emergent limbs beyond their elastic limits, especially those already compromised by internal decay. One such limb, part of a towering emergent fig whose basal flare had been flagged in the earlier survey, had been marked Watch because its cambium layer had small patches of fungal colonization. The decay was internal, a soft rot from an endophytic fungus that lived in symbiosis and, in conditions of stress, expressed weakness in structural wood before external indicators appeared. On a humid afternoon, when the forest's usual clamor folded into a heavy silence between rainbursts, Tico was on his slow, deliberate patrol. His path took him along a high secondary branch of the ceiba, a limb that had, by virtue of its position, borne some of the bridging load from adjacent trees through an overgrown tangle of vines. His weight, distributed in small increments, had little effect, except that he had decided to grope toward a tender cluster of leaves that required him to shift the balance of his entire body. The branch, aged, water-saturated, and harboring microfissures from seasonal expansion and contraction, had never experienced a rapid load change. Tico's movement was the kind of gradual pressure that, in theory, should have been benign. In practice, the slow flexing of the limb nudged an internal crack to propagate. With the slowness of a glacier's edge, the limb began to split. A fine, rising creek propagated down the fiber networks embedded earlier in adjacent members. Rahul, in the platform's microlab, was monitoring a set of distributed strain readings while sipping bitter coffee. The acoustic sensors had been calibrated for subtle wood whispers, low-frequency, ultrasonic vibrations that signaled internal microfracturing. The software had been trained to raise flags on patterns deviating from the diurnal stretch-and-relax cycle. At first, a single node near the ceiba's midsection registered an unusually sustained frequency, a gentle resonance that didn't decay as usual. Lila's screen flashed. She had flagged that signature as one of the early templates for partial delamination. She pinged Jana. Jana, there's a slow ramp here, like creeping shear in the mid-ceiba. It isn't violent, but it's persistent. Check the east anchorage. I'm seeing microscopic displacement trending upward. Jana, out on the observation walkway, was tightening a redundant guideline across to Tower 3 when she felt an almost imperceptible sag at the far anchorage. Her eye flicked to the tension gauge. Its dial was creeping, not in spikes, but in that dangerous, steady drift. She radioed Elena. Elena, I'm seeing load redistribution in the east line. Something's shifting slow. I'm going to go up the short Canopy bridge and look at the ceiba anchor. Lila, keep an eye on that acoustic tag. Rahul, can you cross-check the humidity versus the internal pressure trend? Before either could reconcile what was happening, a sound cut across the silence. A long, drawn-out crack. Not the explosive snap of a sudden failure, but the reluctant giving of wood under a slow, sustained stress. The secondary branch carrying Tico's weight split relatively cleanly. A section, thick with epiphyte growth, started to splay outward, its fall arrested almost theatrically by a cluster of tangled lianas that had for decades connected it to the massively compromised fig limb further away. The falling branch brushed and tugged at several tensioned vines, transferring kinetic energy through the network. Tico, unmoved by the break in speed, found himself sliding a short, controlled distance as the broken piece shifted his grip. He reoriented, his claws finding purchase on an adjacent support, and padded over as if nothing had happened, his slow breath indifferent. The broken segment, however, did something else. It pulled at a set of lianas that had been sharing load with the emergent fig limb under the fungal infestation. Those lianas, now twisted and tensioned by the falling branch, momentarily relayed a force transfer that reduced shear stress in the dangerously compromised limb. The redistribution was ephemeral, but it bought the system a few crucial heartbeats. Jana, arriving at the anchor, and Elena, following with the portable analytics rig, saw the faint shifting mass. Elena's trained eyes went first to the fig's distant crown, where the network of tension lines intersected. That crack in the ceiba, did that just relieve the connection over there? She asked, eyes tracking the subtle sag in the fig's extreme limb. Rahul, squinting at the real-time model, whispered, the load vector in the fig's outer wing just dropped by 15% in under 10 seconds. Whatever just happened up there pulled part of the shared tension away. That could have been a precursor to a cascading failure if the fig's limb had gone suddenly. Tico broke that small branch, and by doing so, he shifted the network, like a slow fuse releasing before an explosion. Lila's system, designed to interpret the acoustic fracture signature as an early warning placeholder, issued the alert. Pattern match, slow partial delamination in support network. Imminent cascade risk, investigate. The team now had a concrete signal. The Sloth's slow branch break, so innocuous in appearance, had become the triggering event that exposed the deeper, hidden hazard. The fungus-compromised fig limb and the tension relief both delayed its catastrophic release and forced their attention toward it. They had at best minutes. The storm front crested the ridge, and the wind began to push the emergent crowns in harmonics that their sensors described as amplification. Elena barked orders. Emergency reinforcement. Jana, rig a supplemental brace to the fig's outer limb, double the dampening on the east line. Rahul, get a sample of the decayed tissue. I want to know the extent of rot. Mateo, mobilize the watch teams on the lower terraces. If that limb lets go, we need evac routes open. Tico, now chewing lazily on a vine, paused for a fraction, turned his head toward them with eyes that had the unfathomable depth of something that observed time differently, then resumed his slow meal. He had, by moving almost imperceptibly, done more than shift wood. He had, in his inertial path, set in motion a series of human responses that might be the difference between a research team's survival and a collapse that would rewrite their models in tragedy. The forest, in its layered complexity, was never simple. The slowness of the branch break had hidden the magnitude of the risk. Without the distributed sensor array, the initial drop in load in the fig limb would have gone unremarked until the big moment of failure, which, under the force of the upcoming storm, would have been violent. Instead, what the team had gotten was a whisper, a slow mechanical release that allowed them to sequence a response. Jana had always approached trees like mechanical trusses with organic skin. In her previous work, building suspension observatories over glaciers and desert canyons, she had learned the virtue of dealing with unpredictable material behavior by increasing redundancy, creating controlled failure paths, and valuing early micro-failure indicators over catastrophic surprises. Here in the breathing forest, the redundancy was latent in biology. The web of lianas, root tension, epiphyte networks. But the unpredictability came from living decay and growth. The branch Tico broke was secondary, its fall deliberately slowed by its tangle with vines. It acted as a low-energy damper, buying the team a fraction of a second to see that the structural integrity of the adjacent fig limb had shifted. The fig's failing limb had been bearing its own weight, plus that of several mist-laden epiphyte mats, and a network of strangler figs and vines had linked it to neighboring trees, creating force chains that amplified load in treacherous ways. Fungal degradation had hollowed the interior, softening core fibers while leaving the bark superficially intact. The limb was approaching a critical shear zone, where internal fiber buckling would have cascaded into a brittle break and the release of its entire mass, tens of metric tons, into the canopy below, possibly detonating adjacent trees in a domino of snap and fall. The team's real-time finite element style biomechanical model, fed by the strain sensors, showed that if that limb failed while the storm's gusts pushed in phase, the dynamic impulse could have sent the platform swinging, shearing its secondary ties and dropping a segment of the observatory into the forest below. Elena, at that point, didn't waste breath. She directed the team to execute what they called the slow stabilization sequence. Jana and Rahul climbed up the network using the rope bridges, their harnesses crawling along with the agility of practiced vertical engineers. Jana's hands moved with precise economy, clamping temporary reinforcement cables, smart, self-adjusting tensioners, around the weakened joint of the fig limb, tying them to adjacent healthy emergent trees. The idea was not to over-constrain and create additional stress, but to redistribute and dampen. She deployed a friction-based pulley system that allowed the limb-limited movement while absorbing the worst of any sudden impulse. Rahul, meanwhile, sacrificed his planned detailed survey of leaf area indices to take inventory of the fungal colonization. He carefully sampled the decayed wood with sterilized tools and collected spores on glass slides. Microscopically, the fungus exhibited a form of white rot that had invaded the lignin structures, eroding cross-link density and increasing compressibility under wet conditions. The rot exhibited a rhythmic, seasonal pattern of aggressive softening triggered by high humidity, an ecological cost of keeping water while maintaining growth. The team's models updated the decay rate in real time and projected that, without intervention, the limb's failure probability in a full storm gust cycle would cross the 80% threshold within the next 36 hours. Lila and her code, however, were doing more than watching numbers. The acoustic profile of the earlier slow break, once thought to be an anomaly, became the seed pattern for a new classifier. She and Elena replayed the waveform, comparing it to the brittle snap of dead branches in previous datasets and the smooth environmental bass of the forest's breathing. The broken branches creak had been a low-frequency crescendo, followed by a subtle shift and then a plateau, what she termed the Sloth signature, because of its association with Tico's methodical movement. The team hypothesized that organisms like sloths, by their slow movement and interaction with the tree's flexible anatomy, might inadvertently interact with marginally stable elements in ways that exposed hidden weaknesses before they released catastrophically. That hypothesis, nascent and speculative, had a practical use now. They layered their monitoring system to weigh future similar signatures more heavily as potential early warning flags. Mateo, coordinating the local watch teams, brought in a small circle of indigenous youth who had grown up under the canopy, boys and girls who could, with a glance, tell when a tree sounded stressed from the ground by hammering their palms against buttress roots and feeling micro vibrations. He instructed them to stand further out than before, listening for low rumbling and watching the underside of the failing limb for any shear plane propagation. He told them the story in their own language. The slow break was a breath. The big tree held because another released a little. They accepted it not as legend but as nuance, filing the experience into their living knowledge. The storm hit 2 days later. The wind came not as a single dramatic gust, but as a series of pulses riding the mountain's ridgelines. Long, sucking pulls, followed by heavy pushes that switched direction with an unsteady frequency. The reinforcements Jana had installed flexed under load. The smart tensioners responded, bleeding energy into adjacent tree masses. The fig limb, now under the new damping constraints, oscillated instead of shearing. The extra cables and redistributed loads prevented the resonance from aligning with the storm's phasing. When the wound in the limb finally failed, it did so quietly, a slow internal separation that forced the upper mass to sag and then settle lower, its fall directed harmlessly into a tangle of pre-positioned sacrificial softwood catchlines and away from the main platform. The heavy impact created a shockwave that rippled through the canopy. Vines rattled, epiphytes shivered, but the observatory remained intact, quivering but alive. Later, when the wind died off and the rain softened into a fine mist, the team gathered on the platform, wet, exhausted, and slick with adrenaline. They had been spared by an unlikely chain, a sloth's slow shift, a creak that became a warning, quick human response, and an engineered redistribution. Tico, high above in his ceiba, had watched the entire sequence with the impassive gaze of one who had known the forest's weight all along. He had, at his pace, intervened without intention, and the forest had, through the web of its anatomy and the team's attention, turned that intervention into salvation. The calm after the storm turned into a focused period of analysis. No longer could the team treat the sloth's involvement as a poetic aside. The mechanics demanded a deeper understanding. Elena proposed a formal sub-study, incidental biomechanical signaling in arboreal systems, sloth-tree interaction as early warning. She, Rahul, and Lila wrote a supplemental grant addendum on the spot, using sketches from the field and waveforms from the acoustic event as initial evidence. Jana, not one to romanticize, insisted on coupling that behavioral observation with rigorous mechanical modeling. The falling branch had not only created a signal, but had acted as a dynamic buffer. She ordered the deployment of controlled microtests on similar secondary branches in adjacent emergent trees to test how deliberate minimal load triggers could be used to gently de-stress compromised limbs before catastrophic failure, essentially mechanizing a slow break protocol. They mapped the force transmission path that the broken branch had initiated. The Liana network's topology revealed it functioned like a series of nonlinear springs. When the secondary branch shifted, tension in the adjacent network redistributed in a highly localized way. Kurtosis in the load distribution had temporarily dropped the critical shear in the susceptible fig limb. Jana used 3D scans to build a physical analog in their lab, a scaled composite model of emergent limb linkages with embedded dampers that replicated the sloth-induced shift. In simulation, introducing a slow, controlled release in similar secondary members, analogous to what Tico had done unwittingly, lowered failure probability in compromised primary limbs by up to 40% under similar storm loading. Maya, one of the indigenous youth who had now been taken under the team's informal apprenticeship program, visited Rahul during his fungal analysis. She had observed in her own family stories that slow movement was always associated with caution, that the animals who took their time were the ones who felt the forest's bones. She suggested they record the time of day and conditions when sloths like Tico moved at the pace they did. Was the slowness itself a form of distributed sensing? Rahul added environmental context, temperature, humidity, canopy drip rates, and their correlation to sloth shift behavior. Lila's sensors, adapted, began pulling sloth-influenced micro-oscillation patterns and correlating them to subsequent structural anomalies across their instrumented network. In the meantime, Elena arranged for a detailed health check on Tico via remote observation. They had learned from the villagers that sloths occasionally had small infections or arthritic stiffness that changed their movement patterns. Tico had a slight swelling in one forelimb, an old injury that adjusted his pathing along the branch's surface, the same path that had caused his slow, uneven transfer of weight minutes before the break. The team noted the convergence of conditions, the fungal degradation weakening the fig limb, the saturated soils increasing whole tree fluid inertia, and Tico's subtle shift altering an otherwise marginal force vector in the support network. In their published preliminary note, they would later phrase it more carefully. A constellation of slow biological interactions intersected with latent structural weakness to produce a pre-failure signal event. In private, among themselves, they called it Tico's warning. The awareness expanded outward. A neighboring research team studying avian nest site selection heard the story and visited to see if the network of birds, which often shifted perching behavior before storms, could be integrated into a multi-species early warning overlay. The forest, already a system of redundancy, began to show its depth. Sloths, birds, root tension monitors, and hydrological observers all contributing pieces of a puzzle that with enough pieces could turn catastrophe into manageable disturbance. Months later, the seasonal winds returned, but the forest's collective vigilance had changed. The team's augmented early warning system now included calibrated slow break triggers, acoustic pattern recognition for the sloth signature, fungal decay progression indexing, and the social network of local watchers who could, from ground level, sense subtle shifts across buttressed roots. The fig limb, while still compromised, was now part of an adaptive damping grid and no longer a single point of failure. The next storm arrived with unexpected intensity. A rain slip higher up destabilized a section of the ridge, sending a pulse of water down subterranean pathways that increased the local water table temporarily. Wind gusts angled differently, striking the emergent crowns in phased clusters. A group of younger sloths, perhaps related to Tico, were moving in the canopy that morning, each path flagged by Lila's software as they negotiated the same secondary branches that had shown prior utility. One adolescent sloth, smaller and more restless, duplicated the earlier sequence, crossing a high secondary feeder branch and causing a minute flex that generated a low-frequency creak. The system flagged it. Jana, watching the new waveform overlay, recognized the pattern before the big event and activated an additional reinforcement protocol further upstream. She redirected a portion of the load by pre-tensioning a new tether system connected to a cluster of healthy emergent strangler figs. The original fig limb, this time, faced the storm's core in a different phase. The pulsating forces had built to a pattern that, without intervention, would have aligned with its natural frequency. Because of the earlier expansion of the damping grid, and because the system had learned to accept input from sloth-induced microalerts as prep time, the limb's potential failure hit a system already flexed for resilience. When the internal rot finally surrendered, the fall was not a collapse into chaos. It peeled away in a controlled slide, guided by newly installed sacrificial deflection nets, and landing in a pre-cleared tangle that channeled debris toward a vegetated basin instead of the research station. The younger sloth's micro-break didn't avert the failure this time, but its signal, layered atop the previous knowledge, ensured the failure was survivable, predicted, and the worst-case scenario avoided. The team, in that storm's wake, recorded the event with awe. They now had a sequence. Tico's slow break triggered awareness. Engineered damping prevented early collapse. Subsequent sloth behavior reinforced the system, guiding adaptive response that shaped the later failure into a non-catastrophic release. This became their most cited case study in internal training, a layered test of how living systems' seemingly trivial behaviors could cascade through engineered networks. The story of the sloth who broke a branch and saved the platform was no longer a whisper between them. It took form in formal presentations, in the curated case file labeled with the affectionate moniker, the Slow Sentinel event. Regional ecological agencies assigned a small working group to codify interspecies early warning systems. The idea was not to fetishize the sloth. They had no desire to harness or manipulate Tico for data, but rather to integrate his type of movement as a complementary layer. Times when deliberate animal motion intersected with marginal mechanical instability to create pre-failure cues. They created a small interpretive field module for visiting students. The module included side-by-side displays, one showing the structural model of limb shear and failure probability, another playing the audio waveform of the original sloth signature, and a third overlaying the treetop video of the slow branch break juxtaposed with the network response. Children from the mountain villages came, wide-eyed, to press their palms against the tactile model and say the words in their own language. The slow one warned us. Elena insisted the plaque at the base read simply, Tico's branch moved like a pause. That pause gave us time. The scientific papers that followed were careful. Incidental biotic interactions as early stress indicators became a subheading in a broader review. Funding flowed not just for Canopy observatories, but for low-cost community sensor integration, pairing local trackers with acoustic, biological, and mechanical data fusion. The sloth's movement inspired a new class of soft pre-failure actuators that emulated his slow weight transfer, mechanical analogs that, when introduced artificially to stressed networks, could gently relieve and test marginal connections without triggering full-scale cyclic fatigue. Tico, in his slow orbit above, remained unimpressed by scientific accolades. He tuned his slow movements toward eucalyptus leaves or some other favored snack. Yet the forest's watchers, the kids and the newly trained apprentices, kept an eye out whenever he climbed to a new perch or shifted more than usual. They'd call down to the platform, Tico's moving. That phrase had become a quiet alert, a context-free signal that prompted a quick scan, a check of strain gauges, a moment's acknowledgement of the interconnected breathing of the canopy. The indigenous communities near Sierra Verde had always spoken of the forest as a web of voices. After the Slow Sentinel event, their stories added texture. Some elders began to tell the children that the slow ones hear the cracks before they sound, and that the animals who took their time carried a patience that could be translated into human vigilance. The research team, who had once approached the forest with instruments and models alone, began formal joint workshops on integrated observation, where ceremonial listeners worked side by side with engineers in data workshops, annotating digital dashboards with oral histories and observed animal behavior. A small conference at the regional university had a session titled From Sloth to System: Living Warning Layers in Complex Ecosystems. Elena gave the keynote, emphasizing humility. We went into the forest thinking we were observing it. The forest has been observing us. Tico didn't save us with intention. He only ever moved slowly, as he always had. But we learned to hear that slowness. That's the difference between a model that predicts collapse and a system that survives it. Jana presented the engineered analogs, and Lila showcased the updated machine learning classifier that now included sloth-weighted early warning heuristics. A small group of engineers from urban infrastructure fields attended, scribbling notes on how slow break analogs might preemptively relieve load in aging bridge cables or in warming permafrost systems, slowness as a tool rather than lethargy as vulnerability. The research grant that had first funded Canopy observatories was renewed with a new clause. A portion of funding was earmarked for living sentinel research, the study not only of sloths, but of other slow-moving, behaviorally consistent species whose interaction with stress points could provide pre-failure signals across ecosystems, from alpine rock outcrops to tidal marsh routes. Years later, the observatory above the canopy had grown into a resilient node in a broader network. The original platform that should have collapsed under the FIG's limb failure had become the reference anchor for best practices in bio-aware structural monitoring. A small wooden plaque hung near Jana's anchor station, carved by Maya and the village youth, in honor of Tico, the slow sentinel. He moved too slowly to be noticed. That slowness made us listen. The canopy still breathes because of a pause he gave. Tico, older now, still moved with the deliberate grace of his species. He had new kin, some of whom would occasionally traverse the same secondary branch that had once mediated the critical load shift. The system had evolved. A generation of field trainees learned to listen for sloth creaks as much as they learned to read strain gauges. The phrase Tico's pause became shorthand in their logs, not for mysticism, but for the essential operational meaning. A small, slow anomaly that deserved attention before it became a crisis. On an early, clear morning, a young graduate named Amara, part of the new cohort, sat beside Elena. The forest was quiet but alert. Far above, a sloth had just begun a deliberate stretch that caused a faint wood whisper on the distributed acoustic display. Elena smiled and tapped Amara's tablet. See that? Pause the data. That's the same signature we got years ago. It's not that the sloth is saving us again. He's showing us what our models still don't fully understand. We still have work. The rainforest, as always, continued to shift. Branches broke slowly, limbs failed, storms came. Yet now, whenever a sloth moved with slightly more deliberation, a ripple of awareness went through the observatory, and a small human hand tightened a tensioner, postponed a failure, or rerouted a platform. The unbelievable moment when a sloth's slow branch break averted a jungle canopy collapse became not an isolated miracle, but a foundational story in the ongoing conversation between the living forest and those who sought to study and survive within it.